Okay, full screen. All right, so when it comes to k-means, what's happening here is that what we've seen so far is that there's some sort of cost function that we want to minimize. So when you take a look at all these clustering configurations, there's different clustering configurations. You can see which one is the best clustering configuration or the labels of the centroids to choose. So to figure out what those are, we have to define a cost function or a distortion function that will be able to do this for us. So in k-means, we seek to minimize this cost function where it will provide the best centroids and the best labels for all the examples and with the least amount of spread or the least amount of error for all examples. Okay, so recall the notation C superscript I. This is the cluster, so it's between 1, 2, up to, okay, right? Which example I belongs to. Okay, or specifically, let me just do, okay? And then, let's see, mu k, this is the cluster centroid, which is associated with example I. Okay, so as I talked about, what you can do is when you see the output of the algorithm, you can represent each example in that cluster to be the actual cluster centroid itself. So finally, this notation, mu c of I, what this means is that it is the cluster centroid for example I that is associated with that example. So this is the cluster centroid. I want to establish this notation so I can talk about how the cost function is going to work. So the cluster centroid to which example, xi is assigned to. Okay, so just a small example. Okay, so if C of 3 is 5, what this means is that if example 3 is assigned to cluster 5, therefore, okay, so this is saying that this notation here, this is saying that when you take a look at example 3 belongs to cluster 5, so I want the centroid that is associated with example 3, which is the 5th centroid. Okay, so that's what that means. All right, so example x of I belongs to cluster 5. Therefore, use centroid 5. So that is the centroid that is represented for that particular example for number 3. Okay, so the cost function is going to look like this. So the parameters that we have are the labels. So we have m labels. Okay, so we have m labels, one for each example. And we also have k centroids. So this is actually very easy. Not too much, just sum them up. Okay. So this is the cost function. If you stare at it for a while, it actually makes sense. So what you're doing is for each example that you have, what you want to be sure is that that example is as closest to that particular centroid that example is representative of. So what you're doing is for each example that you have, find the distance with that example with this representative cluster centroid. And when you sum up all these distances, the configuration that gives you the smallest distortion per term is probably the best cluster assignment or the cluster configuration you want to choose. Because you want to minimize the distance between that example with this representative cluster centroid. So minimize the sum of all those distances. Whichever configuration gives you the smallest of all those sums, that is the configuration that you choose. Okay? So we seek to find the labels for I is equal to 1, 2, all the way up to m, and the centroid configurations, as many as we have k, okay, to minimize distortion. So if you actually stare at it for a little bit, it actually does make sense. Okay, so that's the thing we want to choose. And then in practice, we usually choose K to be less than M. It kind of makes sense. So when you choose the number of clusters that you want, you usually choose it to be less than the number of examples that you have, which, well, if let's say you had 10 examples and if you choose 10 clusters, well, that doesn't make any sense. You can just consider 1 point as the one cluster and that's it. It doesn't give you anything meaningful. So you usually choose the number of clusters to be less than the number of examples that you have. So, you know, just putting it out there just in case. So in practice, we usually choose the number of clusters to be less than M, and then just want to put that in. And now here we go with the problem with random initialization. So this is the problem I kept talking about, and here's a way to try to solve it. Problem with random initialization. So the initial centroids determine what the final clusters look like. Okay? This is what we call local optima. Local optima of the cost function. Let me show you a quick diagram to explain what I'm talking about. So it looks like this. This comes from Andrew Ng's slides as well. Very nice diagram. Okay. Let me just put the source in. Okay. So let's say we have a bunch of these points. We have two features. And let's say for the moment that, you know, we decide to make the initial centroids, you know, here and here and here. So when you actually do the actual clustering algorithm, then these are pretty good, and that's totally fine. But let's say you randomly initialize it such that we have two clusters here and then the one cluster there. So if we actually do the k-means, what's going to happen is that this will converge to this. So even though, so the random initialization, depending on how you choose it, will give you completely different results. Because, you know, obviously we can kind of see that there's three clusters here, right? But what's happening here is that, we choose two initial clusters that are here and then one over there. And when you actually run the algorithm, this is the configuration that you get, which is probably not the best thing to take a look at. And then also we may, you know, choose these set of points. You know, we have an initial cluster here, and then we have one here and one here, and this is the result that you get. So depending on the initial configuration of the cluster centroids, it will give you completely different results, as you can see here. So depending on which one you're looking at, it will give you different clustering results. So given random centroids, you know, choose from the examples. That's what we'll usually do. We could end up with different results. It's possible. Sometimes, you know, you may get away with choosing, you know, random ones, and then depending on the randoms, you might get the same configuration. It just depends on the data. Come on. Okay. So what we're going to do here is to get the best results. The best way to do this will be to run k-means several times. And then so after you run it the first time, you calculate what the cost function would be. Then you run it the second time, calculate what the cost function would be. You run it, you know, several times, and whichever configuration gave you the lowest cost, that is the configuration you choose. Okay, so that's the best way we do it. That'll be a way to get out of this local optima stuff. All right, because you know, if you do it 100 or 200 times, there is a high chance that you will finally get to the point where it has the best configuration because you're rerunning it many times. Okay, so to get the best results, run k-means several times. Okay, and choose the configuration with the lowest distortion. Okay, so that's basically what you do. So here's the final algorithm. So this is the final k-means algorithm we're going to take a look at. Okay, so you're going to repeat n times. Okay, So typically it's about 100 or so. It just depends on experimentation. So typically n is equal to 100. I like to choose 100. Okay, so you're going to repeat this n times. So 1, you're going to initialize cluster centroids. All right. So what I mean here is to choose, k random examples. Usually we do that, or you can just make them completely random. It's up to you. And you're going to make sure that they're unique. So you don't want two, centroids that are the same. Because what's going to happen is that you'll have a whole bunch of points that are assigned to one cluster and none assigned to the other, and that's not good. Okay, so unique. Okay, 2, run k-means. And you want to get the labels, and you also want to get the centroids for each example. All right, so for I is equal to 1, 2, all the way up to m, we have m examples. And we also want to get the centroids. Okay? Okay. And then 3. Compute the cost function. So we want this, we want the label configuration, okay, as well as the actual centroids themselves. Okay, so compute that, and then we finish here, okay, and then choose the configuration with the lowest cost. Okay, and that's how you do it in the end. So that's the actual algorithm that you do. Also, what this is called? What you're doing is you are, choosing a bunch of centroids, running it, and then finding the cost. And then what you're doing is you're rerunning it several times and finding the lowest cost. This is actually a modification of an algorithm which is known as RANSAC, random sample consensus. So you'll see that in the literature a lot. So it's called RANSAC, or random sample consensus. It's just a little bit of extra bonus. You don't really need to know this, but what RANSAC means is that you sample a bunch of points, the least amount that'll give you what the model that you're looking at, and then you calculate the cost that is for you to use these parameters associated with your points, and then you keep randomly choosing all these points, and whichever points give you the lowest cost, those are the model parameters you choose. So it's actually called RANSAC. Yes. Sorry, what's C? CI. CI is the label for that cluster. I established this notation at the beginning. Centroid is mu.
Yeah, so we have for each cluster we should have one centroid, right?
Correct. So no, we have k centroids and labels that are so what you're doing is each example is assigned a label and ultimately a centroid. So you have example 1 is assigned, cluster 5, and then centroid 5 is associated with that cluster. So you have a label information and centroid that is associated with each example. Okay? All right. Okay. All right. So that's it here. Okay, so let me just get onto this quickly and then we'll continue. So choosing number of clusters. If you're still unclear, you can talk to me after, because you probably came a little late and I established notation. Okay, so choosing the number of clusters. So this currently is an unsolved problem. It's actually known as what's called an NP-hard problem. So choosing the optimal number of clusters to cluster your data, there is no known algorithm to do it. Unfortunately, it's subject to experimentation. So you have to try a bunch of numbers and see what the distribution looks like, see what the cost looks like, and you choose the cluster that makes most sense to you, or the number of clusters that make most sense to you. Okay, so this is an unsolved problem. Okay, so we know no reliable method to automatically choose. Choose this. Okay, so there is a heuristic that you can use which sometimes will work and sometimes that doesn't. One method, heuristic, that is used is called the elbow method. And I'll talk about why it's called elbow method in a little bit. It's called the elbow method. So what the elbow method is that what you do is you start off with one cluster, calculate what the cost would be, and then you go with two clusters, calculate what the cost would be. So you are plotting this on a graph where the horizontal axis is the number cluster you choose, and the vertical axis is the cost, the final cost at the end. And you choose the point where the graph dips like an elbow, where once you introduce a certain number of clusters after that point, the cost doesn't really decrease. It doesn't really decrease by a certain amount. So that point, that apex, is what is known as the elbow, and you choose the number of clusters to be where that elbow point is located. Okay? So what you're doing here is run full k-means and keep changing number of clusters. You start off with 1 and then 2 and then you keep going. Okay? And keep changing the number of clusters, and then what you have to do is you have to remember the costs associated for each assignment. Come on, go to the next page. Thanks. Okay, remember the smallest distortion for each run. Okay, and plot on a graph. Plot graph of distortion versus number of clusters. Okay, and let's see here. So you do that and then find the point where adding another cluster doesn't really make the cost function decrease as much. So adding one more cluster doesn't decrease cost as much. Okay, so it looks like this. It's defined as the elbow. So it may look something like this. So you've got, this is the number of clusters. Okay, so 1, 2, 3, 4, 5, 6, for example, and this is the cost, J, and it might look something like this. So you've got, the cost is high for 1, the cost is high for 2, and then it may dip somewhere here like this. So it might look like this. Okay, so here is what's known as the elbow. All right, and in this case, this is where k is equal to 3. But this doesn't happen all the time. That's why it's called a heuristic. Sometimes it works, sometimes it doesn't. It just depends on what the data looks like. Okay, so warning. It doesn't work all the time. But it's something to try first if you wish. All right? Okay? And that's all I have to say about that. That is it for k-means, all right? Okay, now we're going to get into the next topic, which is a very fun one. It's dimensionality reduction. Probably one of the coolest applications of unsupervised learning that's out there. Oopsie. Okay, so dimensionality reduction. Let's say you've got a data set with thousands or maybe 10,000s of features, right? It might be a little unmanageable. And let's say you want to create a prediction model that will take in these features, and you notice that it takes a very long time to train. Like, training a model with tens of thousands of features might take a very long time. So maybe what you want to do is you might want to reduce the number of features that you have to make the training go a little faster. So instead of using 10,000s of features, you might want to reduce it to maybe 10 or 20. So one way to do that will be to systematically eliminate features and try to retrain your model, but that takes a long time to do. So what you can do instead is you can take your data set and reduce the number of features automatically to scale it down from 10,000s to maybe 20 automatically without you choosing the number of features that you want to eliminate. Okay? You also may want to take a look at what the data set looks like. So if you've got a feature, if you've got a data set that might be in 10,000 features with 10,000, dimensions of 10,000s, maybe you want to take a look at what it would look like in the physical world. So you want to reduce it down to maybe 2 or 3 dimensions, and you can plot it on a graph and see what it looks like. So motivations for dimensionality reduction would be to compress your data set. It's a compact representation of your data set for you to maybe plot your data, and also perhaps to compress the data so that you can train your algorithm a little faster. Okay, so that's the whole point of dimensionality reduction. So suppose we have a data set with, you know, a lot of features. Okay, you know, and then if we want to train a prediction model, it can be regression or classification. It depends on what you know, use case you have. Doesn't matter what, you know, whichever one you want. Okay, it may take a long time to train. You also probably don't have enough memory to do this. You know, if you have, you know, millions of features, then you probably don't have a computer that will be able to handle this kind of stuff. Okay, so we also may want to visualize it. Maybe we want to see what it looks like on a graph and something that we can physically see. We also may want to visualize the data set, what it looks like. Okay, so the purpose of dimensionality reduction is to take your training data and to find a more compact representation of it for the purposes of either training your system faster or perhaps visualizing it on a graph so we can see what, you know, what the trends would look like. Okay, so dimensionality reduction finds a compact representation of the data set. Okay, using fewer features. Okay, so the goal is that if we have n features, we all want to reduce it down to a set of p features, where p is going to be less than n. All right, so if we have n features, transform the data to p features, where p is usually much smaller than n. It just depends on what the data looks like. So for example, if you had, you know, 10,000 features, you probably want to reduce it down to maybe 20 or 30 or something like that. Okay, so this also allows for data compression too. Obviously, because if you're reducing your data set from 10,000 features down to 20, there's an obvious, you know, there's obvious storage savings associated to that, right? So it allows for data compression and visualization. Okay, so let's take a look at some more, you know, just some graphical examples. So data compression. Okay, so let me just show you a couple of diagrams. So this is from Andrew Yang again, very nice guy. Okay, so let's say the purpose of this, you know, this is the first example. I want to reduce from 2D to 1D, so 2D to 1D. I want to go from 2D down to 1D. Okay, so if you take a look at this, you know, this graph, you have a whole bunch of features, and we see that you know, there's kind of a linear relationship between the features. So with x1 increasing, x2 also increases. So perhaps we can find some sort of line that we can fit through here, something like this, I guess. And then what we want to do is we want to be able to model the same behavior by reducing the number of dimensions. So I'm going to go from 2D down to 1D. So what is a one-dimensional representation of the same trend? So without losing loss of generality, if I were to take all these points and project them down onto this line with the least amount of error. So if I take this example and I project it down to this line, take the example here, if I take all these examples and project them down onto this line, like this, I get this representation here. And you can see that, you know, if I compare between both representations, it more or less follows the same trend. As one feature increases, the other increases as well. But I want to represent the same behavior, but just reducing the number of features that I have. All right, so I'm projecting it onto a new axis, which is called Z1. And Z1 will capture this new behavior, just using one fewer feature. Okay, so what I mean here is that, you know, you have a bunch of examples, you know, this is x1, this is x2, and so on and so forth. And all of these, you know, are using two features. So they're both real valued and they're all using two features. And what I want to do is I want to transform each example to a new space which just uses one feature instead. Okay, So that's the whole point. So before I had, xi, and then after I want to go to a new feature space, zi. So the whole point here is we can see that there is an increasing trend, as x1 increases, so does x2. Okay, so what we want to do is we can reduce this from a two-dimensional data set down to one-dimensional, and still have this and still model the same behavior. Okay, so we define a new axis to capture this. So define a new axis, Z1, to capture this behavior. Okay, so that's a very simple example. So, I'm eliminating one feature, but I'm still able to capture the same behavior as it was before, even though from 2 dimensions down to 1. So that one-dimensional representation covers pretty much the same behavior as if you were to consider in 2 dimensions. So that's a little artificial. Let's take a look at another example. Let's say I want to go from 3D to 2D. This probably is it's a better example to take a look at. Here we go. Okay, here's another example. So if you take a look here, we have a set of 3 features, and if you take a look at how these features are oriented in space, you'll see that they more or less fall along some sort of plane, right? So there's some sort of diagonal plane that kind of looks like this. Oopsie. Okay. So remember, all you need is basically 2 directions to define a plane. So what I can do here is I can define a new set of axes which will cover the same behavior, but we can eliminate one feature altogether. So for example, if I defined an axis, if I call this maybe, Z1 going this way, right, and Z2 going this way, right, and these are perpendicular to each other, if I were to transform this data set, this is what it will look like. So what you're doing is you're perhaps putting some sort of camera, looking down here from this way, and you're visualizing your data set in a completely new method. So imagine putting a camera here, and you're looking down at the training set. This is what it would visualize as. So you can eliminate one feature altogether, and you can still model the same behavior as if you were looking at it in 3D space. All right? So let's see here. So we can see that the points lie on a plane. Okay, we can obviously see that. Okay, so what we're going to do is we're going to define 2 new axes, call it Z1 and Z2, and it's important to note that they are perpendicular to each other. So there's a 90-degree angle of separation between the 2 axes, okay? And we capture the behavior of the system, sorry. The behavior of the data. Behavior of the data in this new system, all right? Okay, so that's not so bad. So that's, data visualization stuff. And so, that's data compression. And then the next application would be visualization, right? So actually, let me just write here. Yeah, that's fine. Okay, that's good. So the next application is data visualization. This will probably be a better example to illustrate. So let's say I have a bunch of, I've got a bunch of examples, and then there's many features associated with it. So example. Okay, suppose we had, the following data about countries around the world. So let me just show you a little graph. Not graph, but a chart or table. So let's say I've got this chart. Okay? So there's different countries on the leftmost column, and you can consider each other column as a feature that represents that particular country. So you have gross domestic product, that's the first feature. And then you have per capita gross domestic product, and then there's the human development index, that's the next feature. You have life expectancy in years, right? And then you have the poverty index and mean household income and all that and so on. And there's so many other features to take a look at, right? So we have countries such as Canada and China and so on. And there's so many different features, or maybe it might be prudent to be able to transform this data set down to maybe 2 or 3 dimensions and see, the trend of the behavior of this data. Give a better perspective of what is going on. Okay, so each column is a feature. Okay, and there are many features. Okay, and we can't visualize beyond 3 dimensions, right? Okay, so it would be nice to be able to shrink this down into maybe 2 dimensions and see what the trend looks like. So it would be nice to transform to 2D and see where countries map. Let's actually see what it looks like on a 2-dimensional representation of this graph, this chart. Okay, so reduce to 2D by dimensionality reduction. So that's the purpose of this. Okay, so what we're going to do is we're going to define 2 new axes. So we'll just do this for 2 dimensions. So what we're going to do is we're just going to take a look at the first 2 features. But then what we want to do is we just don't want to remove all the other features. What we want to do is we want to transform this down into a new set of axes, but taking the other features into account. So we just don't blindly remove the last, we just don't blindly move the 3rd column to the last column. When you're doing dimensionality reduction, you're reducing the data set down to 2 dimensions, but you're also taking the data from the other dimensions into account and reducing it down to a set of 2D features. Okay, so define each country using 2 new axes. Okay, so the first axis will be the gross domestic product. So I'm just going to take X1 and transform that. And then the next one will be the per capita GDP, right? So I'm going to take the first feature, transform that down to a new axis, and I'll do the same thing for the next one. Okay, so if I take everything into account, this is what the dimensionality reduction will give us. This is just, these are arbitrary numbers, but I just want to show you a representation. So what this is doing here is that it's taking all of your data, from the 3rd feature onwards, and compressing it down to a representative set of 2 features that takes all those features into account. So now this looks a little palatable, so maybe we can plot this on a graph. So if we put all these points on a graph, this is what it's going to look like, and we can actually visualize this a little better. It might provide some intuitions, or might provide some insight on how we're actually performing, or how countries are performing. So this is what it looks like. So this is Z1, this is Z2, right? And we can map all the points here. So this is the United States. As you can see here, the first feature is 2, and the second feature is 1.5, which maps exactly to here. And then we can do the rest of it. So this is Singapore, right? This is Canada. Right? This is Russia. I'd just like to point out that these are arbitrary points. So these actually may not represent the true dimensionality reduction, but I just wanted to show you different points. Okay, so this is the GDP, and this is the per capita GDP that's transformed. So if you actually take a look at this, then it might provide some better insights on how we're doing. So, as you venture towards the right and to the top, that means that the country is performing better. So that's actually not bad. Okay, so I just wanted to show you some examples. So let's get on to the actual important question. How do we perform dimensionality reduction? So what is the process to do this for us? Okay, so To do that, we're going to use an algorithm which is called principal components analysis. So I don't know if you've heard it or not, but it's a very popular technique to perform dimensionality reduction. So we're going to use principal components analysis. Or the acronym PCA, which is used quite often in practice, especially amongst data scientists and statisticians. Okay? So the point of PCA is to project the data onto a new representative set of axes that will accurately capture the behavior of your data without compromising the behavior of the data. Okay? So the goal is to project. Project is the keyword that we're going to use in this class. So project the data onto a new set of axes. Okay? These axes capture the behavior of the data. But we're going to use fewer axes than before. Using fewer axes than before. Okay? So what we want to do is we want to project this data onto a new surface like what you saw in the previous graphs that will minimize what's known as the projection error. So you want to find those set of axes where when we take your data and put this onto a new set of axes, the projection error going from the original data set onto this new surface is the smallest possible. We want to minimize what's known as the projection error. Okay? So we find a new surface to project our data. Sorry. Our data. Let me see here. Project our data onto the surface. Okay. That minimizes the projection error. The projection error. Okay. So that's what we want. So we want to minimize the projection error. That's the point of principal components analysis, to find a new set of axes that will minimize the projection error going from the original data set, down to the fewer dimensions. Okay? So I like to make it an important note. The data should be mean normalized before you do this. It's customary to do this. What we mean by mean normalized is that you make sure that the mean of all your features are 0. So what you're doing here is you're going to go, if you have a data matrix, what you do is you find the mean of each column and take each row and subtract by this mean. So when you find the mean of each column afterwards, the mean should be 0. That's what we mean by mean normalized, is that the mean of each feature should be 0. Okay? So mean normalized prior to performing PCA. Okay? So we have to make sure that it's mean normalized. Okay? So what I mean by this is that each feature has a mean of 0. Okay? So how you do this is very simple. All you have to do is just take each example and subtract by the mean of each feature. And that's how you get it to be the mean of 0. Okay? So if the dynamic range is different. So what we have to also consider is that the dynamic range of each feature might vary. So one feature might vary between 1 and 3. Another feature might vary between 1 and 10,000. So mean normalization may not be enough. So you might have to scale by the standard deviation maybe if you want, but we usually just mean normalize. That's what's seen in practice. But you may have to do additional scaling, but that's, that we won't cover. So if the dynamic range of each feature is different, you may have to scale the features too. Have to scale the features as well. By the standard deviation, for example, something like that. But that's the case. But we try to make sure that the dynamic range of all the features is the same. So what I mean by this is that if you want to produce a new feature, for example, I, right? What you want to do is you want to take the original feature and subtract it by its corresponding mean. So that's what I mean by mean normalizing. Okay? So what this says here is for each training example that we have, okay? Sorry, right? And for each feature that we have, okay? So these are the number of features. Okay, this is number of examples. Okay? So what this says here is this is the mean of feature J. Okay? This is the jth feature of example I. And this is the mean subtracted feature of example I. Okay, so jth mean subtracted jth feature. Okay, so all you have to do is just take each feature for one example and subtract each feature by its corresponding mean. And when you do that, you'll make sure that the mean is 0. Okay, so if you want to calculate the mean, it's very easy. All you have to do is just sum over all the examples and just add up the features that are associated with that particular, for all the examples. So that's if that's if you want to put that in, but it's pretty obvious. So just sum over every single example that you have for that particular feature and just average them all. Okay. All right, so that's what we do. So what we need to do here is we have to find the surface that minimizes projection error. So examples. Okay, so let me just go from 2D to 1D for a bit. So let's say I have this graph. Let's say I've got this graph, okay? And then what I want to do is I want to find the surface that minimizes projection error. And I want to go from 2D to 1D. I'm just going to do this graphically, just to be sure. So what we might want to do is we might want to put a line that let's say goes through like this. Okay? So what we mean by projection error is the distance, the perpendicular distance from each example to the surface. So what we mean by projection error is from here to here. Okay? This is what's known as projection error. Okay? So all this stuff. So what you want to do is you want to find this line that minimizes the distance, the projection error over all examples. So we want to minimize projection error. So this might be a good candidate to get the best surface. So this might be a pretty good candidate. Okay? So something like that. So this minimizes, so this is probably a good candidate. But what's not a good candidate will look something, something like this wouldn't work. So something like this would not work. Okay, something like this will not work. So let me just show you the example again, but showing you a bad example. Let's say I wanted to choose a line perhaps something like this. Okay? The reason why this is not good is because when you take each of these examples and project them onto the line, you notice that the distances are quite large. Like, this distance here and this distance here, right? So these are large projection errors. Okay? So this would not work. What you want to do is the goal is to minimize projection error. So this would not work because you have very large projection errors over all training examples. Okay? The goal is to minimize the projection errors. I'll maximize them. Okay? So let me just write some more stuff here. So that's not good. So you probably want something that looks like this. You want a line that goes through it that minimizes projection error. And you're probably thinking, is this related to linear regression? It actually isn't. And I'll talk about why that is in a little bit. But this is actually a different problem from linear regression altogether. But I'll talk about why in a little bit. Okay, so in principal components analysis, these axes define a new surface. Okay? And are perpendicular to each other. That's very important. Okay? Okay, and then what we do is we usually choose P directions. Or not P directions, but P axes, where P is usually less than the total number of features that we have. Okay. So what's happening here is that what we're doing here is we're defining a new axis. You know, this is a new axis. So what principal components analysis means is that we find these new axes that will reproject our data onto a lower surface, and these are what are known as principal axes. Okay, so the actual term for the actual new axis that you're using to define this new projection of data is what's known as a principal axis or principal directions. Okay, so these axes are known as principal axes or principal directions. So it depends on what textbook or what paper or what research you're looking at. Principal axes and principal directions actually mean the same thing. Okay, so you have these new you have this new data, or you have these new axes, and the point is to take your data and project it onto this new surface. So the process of taking your data and projecting it onto the surface, the new transformed data are what are known as scores or principal components. Okay, so the data after it is projected onto the new surface is called the principal components, hence principal components analysis. Or scores. Okay? Also, these are also known as coefficients too. I just want to point that out. Okay, so when you take a look at literature, when they talk about principal components analysis, when they talk about coefficients, they mean the set of new axes that redefine the new surface. And when you take your data and project it onto this new surface, that projected data is what is known as scores or principal components. So there's different, different notation. Okay, so I talked about that. Let me just do one example here. So actually, let me just do that graph one more time. So this is the graph that I have, right? Here's a quick, here are some examples, right? So before I do this, the notation that we're going to adopt, okay, the notation for the, principal axes, we're going to use small case u, not to be confused with mu the mean. So u1, u2, all the way up to up, okay, where p is usually less than n. So u defines what's known as the principal axes or the principal directions. Okay, so I have this graph here, and the best line that minimizes projection error is something like this. And what we want to do is we want to find the direction of where this new surface is going to be. So maybe something like this, for example. So from here to here, right? This defines u1. Okay, so this is the direction of the surface defining the defining the new, I guess not defining the surface to minimize projection error. Okay, so it doesn't have to be in that direction. You can also go on the negative direction if you wish. It's also the same surface, as long as you have some direction that indicates where the surface is coming from. So you can have this. You can also have one going down this way too. It could be negative. Doesn't matter, right? As long as you have some sort of direction that indicates to you where this new surface is. Okay, so this is also acceptable. Okay, still part of the surface. I just want to show one more example and then I'll take a break. Still part of the surface. Okay, and then here's another example going from 3D to 2D. So that's 2D to 1D, right? So let's go from 3D to 2D and we'll take a break. So something like this. Okay, so let's say we've got this data. We can clearly see that it lies on a plane. And then what I want to do is I want to be able to find a new set of axes that will minimize projection error. So perhaps, you know, an axis going down maybe this way, right? We can call this, I guess, perhaps U1, and maybe perhaps this way going U2, I guess. Or, you know, you can clearly see that we can define a plane that we can project our data onto, right? So it doesn't have to be this, but you can actually go the other way too. So maybe instead of going down, we can actually have one that's going up this way, and this is minus, right? And we can have something going this way, which is also minus. So this is also acceptable too. Okay, so we can place these points on the plane. So that's something that you might want to take a look at. So this defines U1 and U2 that minimizes projection error. Okay, so I'm going to take a break here, and then when we come back, I'll finish up PCA and talk about how to actually do this. Okay, so I'll take a break.